Hi friends, today we'll define non-deterministic finite state machine and design some non-deterministic finite state machines. A non-deterministic finite state machine M is equals to K summation delta SA, where K is a finite set of states, summation is an alphabet, S belongs to K is the initial state or the start state. A is a subset of K, is the set of accepting states or final states. Delta is the transition relation, a finite subset of K into summation union epsilon to K. That is, each element of delta contains a state and a input symbol or epsilon pair to the new state. Let us see when NDFSM accepts a string or rejects a string. A NDFSM M accepts a string W if and only if there exists some path along which W drives M to some accepting states. The language accepted by M, denoted by L of M, is the set of all strings accepted by M. Similarly, a NDFSM M rejects a string W if and only if all paths along which W drives M lead to an rejecting state. In the definition of NDFSM, we stated that every element of delta contains a pair of state and input symbol or epsilon going to a new state. So what do you mean by epsilon transition? An epsilon transition is one that does not consume a character of the input string, represented as current state, a transition going to the next state with epsilon as the input. That is, it allows movement from one state to another state without consuming a character of input string. The FSM is non-deterministic if there is at least one state from which there are two or more transitions defined for a single character. That is, consider an NDFSM where we are at the state Q0 and the next input character to be read is A. Then there are three moves that this NDFSM could make. They are, first one is, it can take the epsilon transition to state Q1 before it reads the next input character. Second, it can read the next input character and take the transition to Q2. Or third alternative is it can read the next input character and take the transition to state Q3. So, at given time from state Q0, this NDFSM has three alternatives. So, whether to go with state Q to state Q1 or Q2 or Q3 leads to non-determinism. Let us see how to design some simple non-deterministic finite state machines. Here is a language containing strings of A's and B's having a substring AAB. Possible strings in this language are AAB. After AAB you can have A or B. Before AAB you can have a single A or B or combinations of A's and B's. But compulsory there must be a substring AAB in each of the string. We have already designed DFSM for the same language, wherein from each state there will be one compulsory transition for each alphabet symbol A and B. Let us see how to design non-deterministic FSM for this particular language. First string of this language is AAB. Length of the string is 3. So, the minimum number of states needed are 4. Initial state, having A, B, reaching a final state. So, this is our first string A, B reaching the final state. Let us label these states as Q0, Q1, Q2, Q3, where Q0 is the initial state and Q3 is the final state. So, we have obtained this string, that is, this string AAB is accepted by this particular non-deterministic finite state machine. Then, what is the condition? Before and after this string, I can have any possible number of A's and B's. So, how to design that? So, this is compulsory transition AAB. So, before I can have any number of A's and B's. After, again I can have any number of A's and B's. So, this is how we design the NDFSM for the language having substring AAB. You can see here from state Q0, you have two transitions for the same input symbol A. That is, for A it is going to state Q0 and Q1 also. Another way, you can see here at state Q1 you have a transition for A, whereas for B we don't have any transition in non-deterministic finite state machine. In this language, we have strings of A's and B's ending with substring AAB. Possible strings in this language are AAB, ending with AAB. Before I can have a single A or a single B, AB or BA, or any combinations of A's and B's ending with substring AAB. So, how to design the non-deterministic finite state machine? Number of states needed are 4. Initial state, Q0, input A reaching to state Q1, again from state Q1, A going to state Q2, and again from Q2 for B it is going to Q3, which is the final state. Next, I have satisfied the language, that is AAB reaches the final state. Hence, this string AAB is accepted by this particular non-deterministic finite state machine. So, next, what is the condition? It must end with. It means before AAB I can have anything. So before AAB I can have anything. How do you represent it? So before AAB I have a self loop having any number of A's and B's. But after any number of A's and B's, it must end with AAB. That's it. This is how we design the non-deterministic finite state machine for the string ending with the substring AAB. Again, for the same language, what if we have the string which starts with a substring AAB? So afterwards I can have any number of A's and B's, but compulsory every string must start with the substring AAB. So how to design this non-deterministic finite state machine? 4 states: Q0, Q1, Q2 and Q3, A, B reaching the final state. So the first string is accepted AAB by this NDFSM. Then what is the condition? It starts with AAB. It means what? After having AAB, I can have any possible strings of A's and B's. So how to represent that? So after AAB, I'll take a self loop to the final state having any combinations of A's and B's. So this is how we design the NDFSM for a string starting with the substring AAB. Let us see how to design a NDFSM using a epsilon transition as an optional substring. The language contains a string which is made up of an optional A followed by AA followed by 0 or more B's. The language is very simple. Summation is AB. So let us start designing the NDFSM. The first part, what it states, the string is made up of an optional A. So how do you represent a string made up of an optional A? So you have initial state going to state Q0, going to state Q1, an optional A, that is what? Either epsilon or an A. So this completes an optional A. It has reached to state Q1, either epsilon or A. Then it is followed by 2 consecutive A's. So followed by 2 consecutive A's. 1A and 2A reaching to state Q2 and Q3. So this part is over. Followed by 2 A's is over. Next, followed by 0 or more B's. It means if it is a 0B, it means your Q3 state will be the final state. If 1 or more, then self loop for B. an optional A followed by two consecutive A's followed by 0 or more B's. How do you represent 0 or more B's? Self loop for that particular state reaching the final state. So this is the NDFSM wherein we have used epsilon transition for optional A. Let us see how to design a NDFSM for a language which uses epsilon transitions for multiple sub-languages. Here is a language containing strings of A's and B's where the string is either ABA or the string length is even. So in this language we have two sub-languages. First language is string having ABA or second language is string length is even. If such type of languages are given, then how to design the NDFSM using epsilon transition? So let us start designing it. This is your initial state Q0. Now we have two sub languages. So what I'll do is I will have two paths Q1 and another path Q2 with epsilon transitions. So this divides the language into two sub languages without consuming any input symbol. That is, without any input symbol, Q0 has reached Q1, Q0 will reach Q2. Now let us take the sub language. So what is the sub language here? W having string ABA. So let us design. We know how to design. For ABA, string length is 3. The number of states needed is 4. Label it as Q3, Q4, Q5. String is A, B, A, reaching the final state. So we have designed for the string having ABA reaching the final state. This language, or one more is there. What it states? The string length is even. String length is even. Already we have designed the DFSM for this. The same way here, string length is even. It means what? Initial state is the final state for string length 0. Then for string length 1, it will be say 5. This is Q6. For string length 1, it will be in the intermediate state. Again for string length 2, it will be back to the final state. So this is for this part of the NDFSM is for accepting the strings of even length, and this part of the NDFSM is to accept the string ABA, and we have taken two paths for two sub languages with epsilon transitions. So this is how we design NDFSM for this particular language. This language contains strings of A's and B's such that some XY belong to A or B including epsilon, and W is equals to X A B B A A Y or W is equals to X B A B A Y. The NDFSM obtained is, you can see here, before these two strings we have X and after these two strings we have Y. So the two strings are, substrings are A B B A A, A B B A A, compulsory transitions reaching the final state Q5. Similarly, B A B A, compulsory transitions reaching to final state Q9. And here X and Y, before and after substrings are combinations of A's and B's including epsilon. It means a self loop to the initial state for A or B and a self loop from both the final states having A comma B. So here you can see one initial state and two final states, as we have two types of strings, X A B B A A Y or W is equals to X B A B A Y. Let us design a NDFSM checking from the end. A language containing strings of A's and B's where the fourth symbol from the last character is A. The possible strings in this language are, from the right, first symbol, second symbol, third symbol, fourth symbol. So fourth symbol must be a A. First symbol can be A or B, second can be A or B, third can be A or B, but fourth must be A only. After that, you may have any number of A's and B's. So how to design the NDFSM for this particular language? From the right, that is final state, you have a state. So this can be A or B. Again, this can be A or B. Again, this can be A or B. Yeah, now what happens? This must be compulsory A. And before that, I can have any number of A's and B's. So see here, from the right, this is the first one. It can be A or B. Second can be A or B. Third can be A or B. Fourth must be A only. And after that, fifth, sixth and so on can be any number of A's or B's. So this is the NDFSM obtained for the language having the states Q0, Q1, Q2, Q3, Q4, wherein the last fourth character from the right is A. Language having the strings of A, B, C, D to Z, but the condition is all the 5 vowels A, E, I, O, U must occur in the string in alphabetical order. The DFSM non-deterministic finite state machine obtained is start state S, a compulsory transition A, after that E, I, O, U reaching the final state. So this is for the vowels in alphabetical order, but the summation is A to Z. So in the initial state, we will be having a self loop summation minus a. After having a, we'll have all the possible symbols of summation excluding e. Next, excluding I, excluding o, excluding u, reaching the final state. And after that, you may have any symbol of the alphabet reaching the final state. A language containing even number of A's or exactly 2 B's. In this language, as we have seen before, we have two sub-languages. First language containing even number of A's, or second language containing exactly 2 B's. So, first what we have to do is, from the initial state Q0, take two paths for both the sub-languages Q1, Q2 with epsilon transitions. Then from Q1, design for even number of A's. Even number of A's means initial state is the final state. So Q1 is initial state. 0 occurrence of A reaches the final state. One occurrence of A reaches state Q3. 2 occurrence of A's reaches final state. 3 A's intermediate state. 4 A's again reaches the final state Q1. So this is for even number of A's. Next, Q2 is the initial state for the sub-language having even number exactly 2 B's. So to represent exactly 2 B's, from state Q2 exactly 2 B's, this is 1 B, another is 2B reaching the final state. Say this as Q4, this as Q5. Now, you can see here in this part, first half, even number of A's, but there is no restriction on number of B's. So hence here I may have any number of B's. Similarly, here they have given exactly 2 B's. We have exactly 2 B's, but there is no restriction on number of A's. So here self loop A, self loop A, self loop A. So this is the DFSM, non-deterministic finite state machine, obtained for two sub-languages having even number of A's or exactly 2 B's. Let us design an NDFSM for the language over summation 0, 1, where all W's such that 2 zeros are separated by a string whose length is 4i for some I greater than or equal to 0. Let us see some example strings of this particular language. If I is equals to 0, then 4 into 0 is 0. So we are left over with 2 consecutive zeros as the first string. Next, if I is equals to 1, 4 into 1 is equals to 4. So these two zeros are separated by a string of zeros and ones of length 4. For example, these two zeros as it is, in between you have a string of length 4, 0, 0, 0, 0, 0, 0, 0, 1 or 1, 0, 1, 0 or 1, 1, 1, 1, so on. So let us design the NDFSM for this particular language stepwise. So what is the first step? All the W's such that two zeros are separated by a string. So first we must have compulsory two zeros. So how do you design a compulsory 2 0? So for compulsory 2 zeros we need 3 states: Q0, Q1, Q2. Q0 to Q1 first 0, Q1 to Q2 second 0. Then, so this represents 2 zeros. Now, next part to be designed is these two zeros are separated by a string whose length is 4i. Now I must design a string of length 4i in between these two zeros. So let us design it. So I'll take 3 more states here. Label them as Q3, Q4 and Q5, where this is the first 0, 1, this is the second 0, 1, this is the third 0, 1 and this is the fourth 0, 1. Now if you see here, we have a string of length 1, 2, 3, 4 in between these two zeros. If I is equals to 0, then 0, 0 reaches the final state. So Q2 will be the final state. If I is equals to 1, then length is equals to 4 in between these two zeros. First 0, then we have a string of length 1, 2, 3, 4, then the second 0. If I is equals to 2, then it will be 4 2s are 8, 0, string length of 8, 1, 2, 3, 4, 5, 6, 7, 8, then ending with a 0. So this is the NDFSM for the given language. So in this lecture, we discussed the definition of NDFSM and designed some of the NDFSMs. Thank you.